Welcome back, everybody, and today we're going to continue on with Chapter 17. Today we're going to start looking at measures of dispersion. Particularly, we're going to look at means and the standard deviation from the mean. What does that mean? Well, really, when you're taking a look at a standard distribution, and we're looking at bell curves, we're looking at other models, ranges, and so forth. What you're looking at is to determine or try to determine who is above and who is below the average. That's really what that means. But it's not just enough to know if you're above or below the average. How far above and below the average are you? And how do others compare when it comes to being below or above the average? So this is going to be a little bit more in depth. We're going to be taking a look at formulas, and go ahead and get your book right now because you're going to need it. I'm going to follow along the book to make it as simple as possible. I'll be drawing from the book as far as the examples, and then we'll go throughout the rest of this lecture looking at the standard distributions, standard deviations, and the bell curve. Okay, everybody, let's go ahead and get started with Wednesday's Chapter 17 version. We're going to be looking at several different things today that you'll need to have your book for. As I said in the introduction, you'll need your textbook to follow along. I'm going to be using the models and the graphs and the formulas that come straight out of the book, and it'd be best for you if you follow along with it. I think it would be easiest not to try to incorporate anything of my own, but just to go ahead and just go through what the book has to say to give you a reference that you can have with you whenever you need it. So go ahead and grab your book, and let's start with today's portion of Chapter 17. Now, when it comes to measures of dispersion, what are we talking about? Well, we're talking about differences between highest and lowest and the average. Now, yesterday we gave you an idea of what the mean and mode and median are, and it's important to know those because that's the average, that's the midpoint normally. And it's not just enough to know what the average is, but how far from the average are you at any given time. It may be your sales, it may be production, it may be anything you want to study. Within every what we call dispersion, you have what's called a distribution, and if you see that here on the slide. Now, within a distribution, you have the first measure of distribution, or dispersion as we call it, and that's called the range. And the range is the difference between the smallest and the largest values of a frequency distribution. Now let's go to the next slide, and you'll be able to see what we're talking about. Now notice here you have two product units. You have A and B. Now both average 200, so those are going to be the same. But I want you to notice something. Look at the figure here, the number for product unit A. It's 196 all the way down to December, which is 202. Now again, the average is 200. But notice here, in product unit B, you have 150. And the end in December is 261. So what you have is a larger distribution, a larger range in product unit B than you do in product unit A. Look at the difference between 202 and 196. You're looking at just a handful there. 6 points or so. But notice here, the difference between 261 and 150 is a lot farther. There's a greater range there than what you see in product unit A. And this is what we're going to call high and low dispersion, and you'll see an example of that here in the next slide. Now notice, with low dispersion, everything is pretty tight. It's just in here, but notice here with high dispersion, when you take a look, and we're going off of the last slide, you notice here how product unit A had just a few differences, whereas product unit B had a larger frequency and a larger value based on the variables. So this is the difference. If we were to plot it on a graph, this would be how they would look on the scale. Now, when we're looking also at measures of dispersion, we also have to look at the standard deviation. A standard deviation really is the difference, or it is the measurement of how far off from the mean you are. And they give you some titles here, some examples here. Variance. It's a measure of variability or dispersion. Its square root is the standard deviation, and we'll take a look at all of that here a little bit later on. I'm getting a little bit ahead of myself with these slides, but these are just some terms that will familiarize you with what we're talking about. You have standard deviation, which is a quantitative index of a distribution spread or variability, and the square root of the variance for a distribution. And again, we'll talk about that here in just a minute. It's the average of the amount of variance for a distribution and used to calculate the likelihood or probability of an event occurring. So that's what we want to look at. We want to look at the probability of something happening. I want to look at the probability of being able to increase sales over a period of time or increase productivity over a period of time. And to do that, I can't just throw it up in the air and hope for the best. I need to be able to use statistical analysis to do that. Now, when we talk about standard deviations, let's say, for instance, you have 1 to 100, and that's your range, and 50 is the mean. Okay, so we have the midpoint, which is the mean, or the median. It's going to be 50. Now, it's not just enough to know that you're above or below 50. It's good to know in what increments are you that distance from 50. And if we were to use standard deviation, let's say every 5 points is a standard deviation. So if we went above, it would be 55, 60, 65, 70. And then if we went below, it would be 45, 40, 35, 30. So this would give us an index, or it gives us some type of numerical plot to be able to judge how far and how much variation there is from the average. When you take a look at upper percentiles of ACT scores and so forth, this is how they put you in the upper quadrants. You scored in the 95th percentile or whatever. These are some of the formulas that's used to be able to determine all of that. So let's take a look at some of the formulas now. And let me go ahead and just get these out. There we go. Now, if you turn to page 417, the first thing we want to look at is standard deviation. And that, again, is how far from the mean, how far are you deviating from the mean. Now, I don't have that in this slide, but I'll go ahead and put it up here, or draw it up here. And again, forgive my penmanship, but you have the deviation, and there's the index, which is just the number for it, is equal to the variable. It could be 1 to whatever, minus the bar mean, which is the mean of the sample. Now, if I wanted to look at, as you see here, for the value of 150 units for product B, for the month of January, the deviation score is negative 50. That is 150 minus 200 is equal to negative 50. So, and I'm going right here off of page 417. For the value of 150 units for product B, you would have 150, which is the number And if you go over here, and in January on page 416, you'll see up in Exhibit 17.5, you will see that 150 is what was produced in January. And then when you go to the bottom of Unit B, you notice the average is 200. So that would be the sample mean, 200. So you would write that out as being 150 minus 200. And that would equal negative 50. And I got a shaky hand because this screen is standing straight up. So just forgive me for the penmanship, but you get the idea. Now next we have the mean squared deviation. Now really the mean squared deviation takes away the problem of having positive and negatives and offsetting it. And the formula, as you see, is the sum of the value of whatever you're measuring, the variable for whatever you're measuring, minus the mean, sample mean, which is x bar, squared, divided by the number of variables you have. So that would be, as you see here, it would be in this case that we saw up here, 150 minus 200. But instead of just going straight forward, you would square that and divide it by n. And that would have the mean squared deviation. And that'll offset the possibility that you will have positive or negative. Now, the variance. Now, variance is used as the textbook indicates in a more pragmatic way. We use it for more pragmatic research, such as marketing and so forth. And the way that we look at the variance, and it's still how far away you are from the mean, you would look at it as the variance, which is this symbol, is the sum of the variable minus the bar x, which is the sample mean, squared, divided by the number of variables minus 1. So that will give you a better assessment of where you're at. If it's 0, then every observation will be in the same distribution as the mean. If the variance grows, you'll see it grow. If it decreases, you'll see it decreases. And as you see here, the variance will grow larger as the observations tend to differ increasingly from one and another and from the mean. So you see here the ability to be able to indicate 0 if every observation in the distribution is the same as the mean. So this gives you absolute 0, the others don't. The variables will grow larger as the observations tend to differ increasingly from one another and from the mean. I'm reading right out of the textbooks. So the variance is pretty much the same thing as the deviation, but it's just used more for getting the ability to have absolute 0, which the others don't, but also to show differences in increases. The standard deviation is the elimination of the drawback of having the measure of dispersion in squared units rather than in the original measurement unit. The formula for the standard deviation is this. The standard deviation is which is this, and as your textbook says, you don't see this part in it, but the standard deviation is the sum, same thing, of the variable minus x bar, which is the sample mean, squared, divided by the number minus 1. So if you take a look at the next slide, which we'll look at here, calculating a standard deviation, and this is what we're all looking at here, and this is what I wanted to try to get you to so that you're not overly confused with all of this. This is the formula right here, this section. Okay, so you have the standard deviation is the square root of the sum of the variable minus the bar x, which is the sample mean, squared divided by the number minus 1. Now, if you notice here, this is x. So you've got that product. You have x minus x bar, which is right here. And then you have x minus x bar squared. Now, what does all this mean? Well, you're going to have, at the very beginning, you're going to take each one of these from each sample, from each x, you're going to take 4 minus the deviation, or excuse me, the mean, the bar x is equal to 0.75. Then you're going to square it, and that gives you 0.5625. You're going to do that to every one of these. And then when you finish, you should have this total here. And that's what we see right here, 13.5. But we're not done yet. We don't want to get the square root yet. We also have to divide it by the number. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's x. And it's in here, but it's x. So you have 8 minus 1 is equal to 7. So you have 13.5 divided by 7. And then you have this product, 1.9286. And then when you do the square root, this is the product that you will have, 1.388. So it's, when you figure it out, and here's what I would recommend you do. I would recommend that you take this exhibit, that you go ahead and write those numbers out and tabulate it yourself and see if you come up with the same here. That's what I used to do in statistical analysis, in research statistics, and it always worked for me. So I would recommend you do that. This is not, it's not difficult in as much as it requires you to follow a step-by-step process. So, and at the end, what do we see? We see a standard deviation of 1.3887 from the mean in each increment. So this is going to be kind of like following a recipe, and that's what I heard from my statistics professor way back, and I'm trying to go from memory on all of this. But he indicated that statistics is like following a recipe. It's where if you do not go in step, or if you miss anything, your recipe is going to be messed up. So if you can follow a recipe, you can do these statistics. But these are the methods that we use to be able to calculate standard deviations. And what we're looking at is how far away, again, are we from the mean or from the average. Okay? Now, let's go to a normal distribution. And most of you know that by the bell-shaped curve. And you've seen them time and time again, and they're here in the book, and we've got a couple in this chapter. Now, a normal distribution is a symmetrical, as you see here, bell-shaped distribution, which is a normal curve that describes the expected probability distribution of many chance occurrences. And as you see here, 99% of its values are within plus or minus 3 standard deviations from its mean. Whenever you see this symbol here, it means plus or minus. Now, IQ scores, when they measure IQ scores, you see they'll have that bell curve, and it'll be plus 3 or minus 3 deviations from what's average. And this is how they supposedly can discover whether or not you're a genius, or if you need remedial work in college or whatever. So you see it does have some important and practical usage to it, but that's what a normal distribution is. Now, a standardized normal distribution It's a purely theoretical probability distribution that reflects a specific normal curve for the standard value that we call Z. And Z-scores really is distribution, but it's used in the bell curve as a standard normal distribution. Now, if you take a look at page 420, they'll talk about Z-scores. They're important because you can translate or transform any normal variable, which is X, into the standard value, which is Z. So if you take a look, and I don't think I have that on these slides. Yes, I do. So I'll take a look at that here in a little bit so that I don't get too far ahead of myself. But this is what you need to know so far about the distributions. What are the characteristics of a standard distribution? Well, it's symmetrical about its mean, and we'll take a look at that. The mean identifies the normal curve's highest point, which is also the mean and median and the vertical line about which the normal curve is symmetrical. And you'll see what I'm talking about. Well, you could probably see it now in the textbook. The normal curve has an infinite number of cases. It's a continuous distribution. That means it can go on and on and on. And the area under the curve has a probability density equal to 1. So it begins at 1. The standard normal distribution has a mean of 0 and a standard deviation of 1. So let's say, for instance, from 1 to 100, 50 is the middle. You would have 51, 52, 49, 48 going in the negative direction, and that's would be the normal distribution for a curve. And there we go. As you see here, and what they use in this case is as your textbook indicates, you have a standard deviation of 15. So 85 to 100 is the difference is 15. 70 to 85 is 15. 55 to 70 is 15. 100 to 115, 30, and so on and so forth. But the mean would be right here. This is 100. Everything going this way is plus. Everything going this way is minus. And what you see here, you notice that this here at the tip does not touch this. That's because it goes on and on and on and on and on. And it does the same thing going this way as well. So this is an example, a picture example of the normal distribution. Now, the standard values used to compare an individual value to the population mean in units of the standard deviation. So this is the Z-score that we were talking about. You have the standard value, and that's equal to the value to be transformed minus the mean divided by the standard deviation. So you have the variable here minus the mean, and it's divided by the standard deviation. And you see here the mean is hypothesized, or it's an expected value of the mean. And we have here is the mean, 0, as we saw, 1, deviation 2, 3, negative 1, negative 2, negative 3. If you remember, we said that the deviation in a standard curve is 1, and you have a value of 0 here. Now, this is why Z-scores are so important, because you can take these disparate curves and you can standardize them to where you can have a standard score for these things. Now, I'll be honest with you, I have never had to use a bell curve. I've never had to use any of these types of statistics, but that doesn't mean you won't have to yourself. So it's important to at least grasp the basic fundamentals of all of this. Now, if you notice here how we could use this. Now let's see how we can do it. If you go to page 421, and I'm going to go here to a blank slide, and hopefully I can write all of this stuff out. Let's go to 421 and read with me. Suppose that in the past, a toy manufacturer has experienced mean sales, average sales, which is, you see the symbol there, of 9,000 units, and a standard deviation, and that's the little sign there, of 500 units during September. Okay, so September, this person sold 9,000 units. The production manager wishes to know whether wholesalers will demand between 7,500 and 9,625 units during September of the upcoming year. Because no tables are available showing the distribution for a mean of 9,000 and a standard deviation of 500, we have to transform our distribution of toy sales, which is X, into the standardized form using our simple formula. So this is how you can use this in business. If I want to know if I'm going to be able to sell that much in the next cycle when it comes around, I don't have much data to go off of. This is how I can do it. So you see the formula here. Z is equal to the variable minus the mean divided by the standard deviation. And that would equal to, okay, now we've got a range here that we've got to work for or work with. We have the low end. I don't expect to sell less than 7,500. And as you see here, sometimes this can be hypothetical. So 7,500 would be my low limit minus 9,000, okay, divided by 500. Now, the 7,500, as you see up here in the paragraph, is the low end, and the average for September, the mean for September was 9,000, so that's where I get the 9,000, and that's where I get the 7,500. This is the low end of what I expect to sell minus the average of what I did sell last September, and when I get the math all done, I see a negative 3.00. Now, let's go for the high end and get our z-score there. The z-score is equal to the same thing. The variable minus the mean divided by the standard deviation is equal to 9625 minus 9,000 divided by the standard deviation, which is 500, and that's equal to 1.25. Okay, and again, my math is not my writing is not the best in the world. And you see here, the negative 3.00 indicates the standard Z for sales of 7,500, while the 1.25 is the Z-score for 9,625. And then, as they said here, you can use table in the appendix, point 2, or you can use figure 1710, and you find that the z-score, when it's negative 3.00, equals to 0.499, and when it is 1.25, the area under the curve, or the probability, equals 0.394. So if we took a look at that, this is what we're looking at, 0.0394, 0.499. So there's a greater possibility, and this is what it all boils down to, folks. There's a greater possibility that you're not going to go above that median, that 9,000. Chances are you're going to go towards the low end. Why? Because there's more shaded area here than there are here. So this is how you can use that. And you see here in the bottom paragraph on page 421 how they rationalize all of that and the percentages and so forth of how they got that. So I'll let you guys take a look at all of that. But really, this is why the statistics are so important, especially when you're looking at a business and you don't know how much to order as far as equipment or products or whatever, or how much to make. This will give you a probability, and that's what we're looking at. We're looking at the probability that what you did last year is not going to be what you do this year. because of the statistics and what we see here, there's a greater possibility that you're going to do a little bit above the 7,500, but not as much as you see over here. And if you notice here, this would be the low end right here, 7,500. All right. Now, as you get more towards the middle, you see this increasing. So the probability that you will get 7,500 is low, especially when you take a look at all of this area. So you're probably going to be close to the 9,000, but you're probably going to be less probable in getting the numbers above 9,000 for next September. So when you're forecasting and when you're looking at what you can buy and the probabilities of your sales and so forth, this is why the standard distribution curve is so important. Now again, the best way of doing this is practicing. There's nothing really that I can impart to you other than just to encourage you to practice these statistics. You don't have to memorize them, but you need to know the formula so that when you have to do it, you'll at least know why you're doing it and why there are means and modes and medians, what purpose they serve, and how much important the deviations are and the plus and the negatives and all of that stuff. That's only going to serve to educate you even better, but also to give you an appreciation of it so that when you're called upon to do it, you'll be able to do so. Today we had a chance to take a look at the bell curve and standard distributions. We saw how people will stack up, or measurements will stack up either above or below the average, and how we can really determine those things. Hopefully we didn't get into too much detail, and you're able to gain at least a better appreciation of how research can help you know where you stand as a business compared to the economy, compared to competitors, compared to just about any variable you want to use. Well, that's all we have for today. We'll continue on tomorrow.